The state pattern. Allow an object to change its behavior when its internal state changes. As your game grows, so does the complexity of your code. You've likely used conditional logic or switch statements to handle a bunch of different possibilities based on the state or data in your game. Code like this doesn't scale very well. The state pattern allows you to have a base class that execute different functionality based on its internal state. The idea is close to finite state machines. In this example, we have a player that will perform different actions based on user input. Currently, we're doing that all in one C# script, but another way to go about it would be to create a separate class for each possible state. Inside each class, we have identical methods that will behave differently. Inside the player controller class, we'll set up a state machine as the property. Whenever a method is called like the update method, the state machine delegates it to the current state. That means whenever a state changes, the object will behave in a completely different way, but at the same time, we don't have to change the base class or use a bunch of conditional logic. We'll start by creating a reusable state machine from scratch, which you can use in any of your projects, and then in the second half, implementing it into the player controller we created in the last video. Remember to leave a like and let's jump into Unity. The first thing I want to do is create two C# classes for an interface that each concrete state will implement and the player base state. I'm going to change the iState class to an interface, and all we really want inside this script are four methods that the player base class will implement. Enter will be called whenever the player enters that state, update on every frame, fixed update on every physics update, and exit just before the player's current state changes to a different one. Now we can go to the player base class, which will implement the iState interface, and we abstract because we want all other player states to inherit from this class. Inside, I want references to the player controller and the animator, hashes for each of the animations of the different states of the player, and fade duration to control how fast to transition to the next animation. From there, we can set up the constructor, which passes in the player controller and animator references as parameters. And finally, we can implement all these methods from the iState interface as virtual methods so that any of the inheriting classes can override them later. With that done, I'm going to move the player base class into its own folder and create three scripts for the transition interface, the concrete implementation, and one for the state machine. The state machine is going to need a list of transitions so that it knows state A can transition to state B. We don't want our player to start falling randomly when he's starting to jump or any other shenanigans. So the transitions will act as a set of rules when changing states. Each transition is going to store the target state to transition into, the condition that must be met for the change to take place, like the jump button being pressed to go into the jump state. In the transition interface, we have the iState field for the target state and a func of type bool as the condition. A func is a C# delegate which evaluates to true or false when invoked, which satisfies our requirement for a transition condition. Now we can implement this interface from the transition class and create a constructor which will pass in these fields as parameters and initialize them. From there, we can finally start creating our state machine. First, we want a reference to the current state, that is the active state, which is going to be of type state node. A state node is going to be a child class of the state machine to help us store all the relevant data of each state. Inside, the first property is the actual state itself. Then we want to store all the transitions the state can change to. Using a hash set, we can make sure there is no duplication. Then we pass in the state from the constructor and initialize the transitions hash set. I also want a way to add transitions by creating a method that is going to add a new transition to the hash set, passing in the target state and the condition that must be met as parameters. Back in the state machine class, we can use a dictionary to store all the different states in the state machine and another hash set for transitions which can happen regardless of the previous state, like the jump state, which can be accessed from the idle state, walk state, or the run state. Inside update, first we want to check any of the transition conditions are met for the current state with the getTransition method, which we'll define shortly. If there are, then we update the current state to the new state using the updateState method. And finally, we can call the update method for the current state, which may or may not have been changed as a result of the updateState method. Inside fixedUpdate, we just have to call the fixedUpdate method of the current state. I also want a public method to externally set the current state of the state machine, which will get the state from the nodes dictionary and call its enter method. From there, we can can define the getTransition method, which is going to return a transition if its conditions are met, by first going through all the transitions in the generic transitions hash set and checking if any of their conditions evaluate to true by invoking the func bool and returning. If none of these conditions are met, then we do the same thing for all the transitions for the current state, and finally, if both are not met, then we return null. Inside the update state method, recall from update that the transition parameters can be null, so we have a guard clause first and return early. In any other case, we actually do have a valid state, so we call the exit method of the current state and change to the new state using the setState method we defined earlier. With that, our state machine just needs a method to publicly add transitions, which I'm going to call add. This is going to take in the current state, the target state, and the condition for these transitions as parameters. From there, we want to get the node for the source state if it exists, or create a new one using the get or add node method. Add a transition to this node with the target state and condition as parameters. In add generic method, all we have to do is pass in the target state and condition and add this new transition to the generic transitions hash set. Finally, in the get or add node method, we first want to check if a node for the state parameter exists using the get first or default method for C# dictionaries. If it doesn't, then initialize a new state node, add it to the nodes dictionary, and return it. With that, our state machine is done and we are ready to implement it into our player controller. But first, we need states for the player. In Unity, I'm going to create two C# scripts for the move state and the jump state. In the move state, this is going to inherit from the player base state class, and we can implement the constructor passing in the values to the base state. We first need to change the animation to the move animation in enter and call the player controller's update movement method in update. The player jump state is pretty much the same, with the only difference being in update, where we call update jump instead. Make these methods public and the errors will disappear. Now we can create wrapper methods for the add transition and generic transition methods of the state machine. But for these to work, we first need to create a property for the state machine which we can initialize inside awake. Also in awake, we can start creating variables for the jump and move states as well as the transitions for both of these states. To go to the jump state, the condition is that the jump timer must be running, and to go back to the move state, the player must be grounded and the jump timer shouldn't be running. Set the current state to the move state and call the state machine's update method in update and fixed update method in fixed update. Back in Unity, we have to set up the jump and land animations. I'm going to create a transition from the land animation to the move animation. After playing around with the values for a bit, our player is finally ready with all the animations and functionalities of a robust state machine. Remember to subscribe if you like this video, and I'll see you in the next part of this series where we will start spawning wild Pokemon.